Cover our first pass through section 2.3, analysis of functions. This video will cover up to the first 10 examples that you'll see on the 2.3 lecture. And to get this kicked off, we started with a hand-drawn function I did, which did nothing more as described a little bit up top. I'm not going to read all the pieces here, but the bottom line was this was describing over a period of 12 hours temperature of an object that I was measuring. And I asked you a series of questions about this graph that I built that's tracking temperature over time. We'll start. When was the temperature increasing? Well, again, I can kind of do a finger check, and when you worked that through, you came back with a series of answers. You told me it was increasing between 0 and 3 hours, between 5 and 6 hours, and between 8 and 11 hours. I said, when was it decreasing? You again noticed, and you gave me your answers in terms of intervals. Over what hours was it decreasing? From hour 3 to hour 5, from hour 6 to hour 8, from hour 11 to 12. I said, when was it equal to 0? You went and you looked at your graph and you told me a couple times. You said at time equals 0, at time equals 7, and at time equal 9, my temperature was 0. If I asked you when the temperature was above 0, what did you do? You looked at everything sitting above my pen, all those intervals of time, from 0 to 7, from 9 to 12. You said, hey, I was 0 greater than 0. And again, we'll talk in a little bit when we go through these problems in a little bit more detail. Yes, granted, it wasn't greater than 0 right at time equals 0, time equals 7, time equals 9. We'll handle that with our interval notation. You'll remember some of that. When you're below 0, what did I ask you to do? Just look for the times, well, between hour 7 and hour 9. That's when my function temperature was below 0. If I said, hey, could you tell me when the temperature went from decreasing to increasing? You probably saw a whole bunch of what we'll call turning points. And if I asked you to identify them, you didn't have too much trouble doing that. I asked you to tell me both the time and the temperature at that time. And you gave me a bunch of points. 3, 50, 5, 20, 6, 30, 8, negative 25, 11, 70. And if I asked you where the largest recorded temperature was, the lowest recorded temperature is, you recognize these 2 points. 11, 70, 8, negative 25. Those were the biggest of the big and the smallest of the small. And so, one other question I asked you is, well, okay, you found an absolute max. What about all these other turning points? And the thing we said is we could treat them as if we kind of narrow our view. Here's a good example. If I narrow my view just between the 2 pens, that thing is a maximum just in its own little neighborhood. And this is something that we'll call a local maximum. So, the key thing to notice about all these things is what? We gave a lot of our answers with respect to time, with respect to the x-axis. And we're going to use that a lot as we walk into analysis of functions. So let's start. I'm going to fill a lot of these in relatively quickly, just in the interest of saving ourselves a little bit of time in terms of how long this video runs. So, we start when we analyze some functions with some real basic stuff. Here's a graph. By the way, does it represent a function? Well, what do? You run your vertical line test. And it certainly does. This thing, hey, a first piece of analysis. I got a real function. Great. Since I do have a function, can I evaluate this function at an x value at 2? I certainly can. There's my x coordinate at 2, my y value, what the function comes back is a 0, the y value. F of 2 is equal to 0. Can I define a domain here? Absolutely. How far to the left, how far to the right? Remember, the domain is always expressed in terms, fix a spelling mistake, in terms of x, range always expressed in terms of y. Well, what's my domain? From 1 through to 6, not including 1 because of the open dot, including 6. Notice parentheses, -1, bracket on the 6. And the range, how low do I go? Well, it looks like I get as low as -3, as high as 2. I hit -3, or I don't hit 2. So very quickly, just looking at a little graph, we can analyze something and come back with a lot of information. Let's keep rolling. In this graph, do I have a function? Well, this is something we'll find out. It's called an ellipse. Number one, it's not a function because it does what? It bombs the vertical line test all over the place. So it's not a function. And since it's not a function, I can't evaluate g of 2. I'll just put NA, no such thing. If I tried to do it, what would I have? Hey, I could take this y value. I could also take that y value when x is equal to 2. And remember, a function can do what? For a given input value, it can only produce one output value. So definitely not a function, definitely can't evaluate g of 2. I have no idea what the answer is. I got two choices. Can't have that. The domain, well, even though this is not a function, it still qualifies as a relation. I have a whole bunch of x and y values. I can still define a domain. It goes from -4 to +4. And since we're not seeing any open dots, those are brackets on both. And the range goes from -2 to 2. And again, the same deal, brackets. Now, down here, we found one more thing, and I'm just going to highlight this a little bit more with my pen. Instead of having something that I can graph, create a real figure, a continuous figure for that matter, I might have something like this. This is called a discrete relation. It's just what? It's just a bunch of points. Each point is considered to be just what? Represented by one of those dots. A dot is what? A pair, x, y. A relation is what? A correspondence between an input value, x, and an output value, y. So this is a real cool relation for sure. And those points, I can't draw a vertical line that will touch more than one of those points. This thing is, yes, it is a function. Can I evaluate h of 2? I sure can. There's my x value at 2, and there's my y value at -4. h of 2 is -4. Now in terms of, I can still do a domain and range, no problem here either. How will I do that? Well, I don't have a graph, so I'm not going to use interval notation. I will use set notation. This is what's called down here a discrete function, by the way, because it only has a certain number of points, as opposed to being a continuous curve with what would be essentially infinite points. So for my domain, all I have to do is list all the x coordinates. -4, -2, 1, 2, and 4 are the other x coordinates. And for the range, just go ahead and list all the y coordinates. I got a -4, a -1, a 0, a 1, and a 2. And I am good to go. So, just a bunch of points, still can be a function for sure. So, let's continue, and now let's start doing some of the more interesting analysis. When is the function increasing? When is it decreasing? Well, I'm going to use my pen here to highlight some of that just along the same lines. Look what I'm going to do. I'm going to identify this area that I've just shaded in red and this area that I've shaded in red. Those are the two intervals where what? Where my function is increasing. And just like I did with that temperature example at the beginning of this entire video, I'm going to give my answer in terms of what? You could pretend this is time if you want, but basically just in terms of the x-coordinate. And when I look, the x-coordinate here, the x-coordinate there, this one is about -1/2, the other is +1/2. And so I'm going to say my first increasing interval is -1/2 to 1/2. Notice that I use parentheses for increasing. Why? Because when I'm making those turns, I'm neither increasing or decreasing at x equal -1/2 or x equal +1/2. So with increasing, decreasing, we're going to go ahead and give parentheses. And then if I look at my second interval where I'm increasing, the second red squiggly area, my x-coordinate looks like it's about 2.5, and it's going to run all the way to infinity. Notice we have arrows here. This function is going up and out to the right. It's very, very steep, but it is moving to the right. So I have two intervals where the function is increasing. The things that I haven't shaded represent where this function is decreasing from -infinity to -1/2, and from what? 1/2 to 2.5. And there we have it. What's the important thing to note? I am giving my answer in terms of the x-coordinate. So when you're talking about increasing or decreasing, your answer is based off the x-coordinate. Now, the next two problems talk about minimums and maximums. And to assist me with that, I'm going to go ahead and go to Desmos and print off, which I've already done, a couple of graphs. So, my first problem, example 5, wants me to do x cubed plus 2x squared minus 4x, and it's asking for where does the function have a maximum and minimum. So here's what that graph looks like. Notice it runs down to -infinity, up to +infinity, both down and to the left, up and to the right. And as I look through this curve, there's a couple points that I highlighted out. You could do this with your TI calculator, find your max and mins using those old skills that you've done in Algebra 1 and Algebra 2. But we're just going to use what the graph already gives us and find out that this point right here, that turning point is at -2, 8. And this turning point is at about positive 0.6, negative 1.5. So let me just go ahead and fix this. Sorry about that. And again, just to kind of a little bit of a rounding error. Now, what do I see here? Is there a maximum? Yeah, there is right here. This is at least within its own neighborhood. Remember, your calculator kind of does this kind of stuff. You say, hey, tell me what, find a maximum. You say, well, give me your left bound, give me your right bound. My pen is kind of doing that. So this thing at -2.8, it does represent a maximum. And this thing at 0.6, negative 1.5, does represent a minimum. Now again, key thing to note, they are minimums just kind of what? Within their own little neighborhoods. These are both going to be called local maximum and a local minimum. And why is that? Because they are not the biggest of the big and the smallest of the small. If you look at this graph, you can see a whole bunch of other points over here that have what? A higher y coordinate. I can see a whole bunch of points over here that have what? A lower y coordinate. But I never hit what would be called an absolute maximum or an absolute minimum. And the reason for that is this end behavior that you are seeing. This function keeps going up and up. It always gets bigger and bigger. It never hits a maximum because this thing is running to infinity. Over here, at this part of the function, my end behavior is taking me down to a y coordinate of negative infinity. You never hit negative infinity. Therefore, you never truly reach an absolute minimum. So end behavior will help you. And as you look at these functions, and we'll do this with our next example, you'll see right here, I do have a maximum and minimum at these turning points. However, they are only local. They aren't the biggest of the big. They just happen to be the biggest thing in their own little limited neighborhood. Now, when I move to my next graph, which was problem 6 here, much more complicated polynomial, here's what that graph looks like. And in this case, what do I notice? 3 turning points at negative 1.6, negative 8.6, right at the origin at 0, 0, and at 1.4, negative 4.4. In this case, what am I going to come to a conclusion on? Well, negative 1.6, negative 8.6 is a local minimum, and for that matter, 1.4, negative 4.4 also happens to be a minimum. One key thing, notice this, and this again goes back to our example. I am providing what? Points. The local min, the local maxes, all these min-max are always expressed as what? X, Y coordinates. They're expressed as a point. Please make that something that you keep in mind. By the way, 0, 0, that serves as a local max. And sometimes you can be the biggest thing in your neighborhood, aka a local max, but you could also be the biggest of the big. So let's stare something down real quick. Let's look first at this point. We've identified it as a local max. It's certainly the biggest in its own little neighborhood. Is it the biggest everywhere? Absolutely not. And by the way, just like in our other problem, what do we notice? The end behavior of this function, turns out on both sides, is running towards what? A y coordinate of infinity. We never hit that. There is no absolute max with this problem. But for an absolute min, what do we notice if you stare down this graph? This, negative 1.6, negative 8.6, it is definitely the lowest of the low, the smallest of the smallest. It is an absolute min. There is no point anywhere on this graph in which the y coordinate is any smaller than negative 8.6. So, key point, you can be a low, all these turning points are locals. And it's possible that some of those locals could be absolute. Just keep that in mind. The end behavior helps you figure out a lot of those pieces. All right, let's continue. And let's move on to our back page, just through example number 7. Bear with me one second as I grab that. Here we go. So, our last piece, 0 in comparison to 0 and end behavior for this part of the lecture. Just like we did with the temperature, there are sometimes when we say, hey, when is the function equal to 0? Well, I can see that at 4 different points. At x equal -1, at x equals 0, at x equal +1, and at x equal 3. The zeros of the function I can say are at x equal -1, 0, 1, 3. When do I hit a value of 0? Just like I did, in the other question, I answered the time when the function was greater than 0, or the temperature was greater than 0. All right, now, where is the function greater than 0? Well, all I really have to do is kind of lay the pen down just like I did the other time and look for everything that's sitting above 0. And I'll do that right here. I'll do that with my little small spot here. And I'll do it with my spot right there. Those are all the places where the function is greater than 0. And this would be what? From -infinity to -1. Notice how I use parentheses because we're looking for greater than 0. So this point I don't want to include. Between 0 and 1, I got another interval. And finally, between 3 and infinity, I have another place where I am greater than 0. If I'm asked for greater than or equal to 0, my answer is exactly the same, except now I want to include those 4 dotted points, the 4 points that represent the zeros, because now I can include being equal to 0. So my answer here is -infinity to -1, with a bracket, union 0 to 1 with brackets, union bracket 3, parentheses, infinity. And for less than 0, I'm just looking at all the other areas, which is what? Between -1 and 0. And notice how I've gone back to parentheses. And between what? 1 and 3. And to answer this question, less than 0, all I got to do is take all these pieces, no infinities are involved, all 4 of these things just turn into brackets. -1, 0, union, bracket 1, comma, 3, close bracket, and I am good to go. So, zeros, just tell me the times, tell me the x values that make the function equal to 0. That's what a 0 would be answered as. In the other cases, what do I say when I'm doing comparison to 0? Greater than equal, less than equal. Always provide your answer with respect to what? To the x coordinates. Just like we did with the temperature example. I said, what times was it above 0? What time was it below? And you gave me the answer from this time to that time. Same thing as an interval notation. All right, we have one more piece to cover, and that is end behavior. I have 3 different functions here, and you'll notice that I've defined them and taken what they've given to me. And a couple of the functions, again, just because we didn't have the capability when we were printing these, I've gone ahead and defined arrows. And in one particular problem where I have a true endpoint, I've not defined an arrow in both directions. I've just done one. And so what we want to do with these types of things, this is the last part of analyzing a function, is to ask what's the end behavior. Now, we certainly can do these with the other things we've had, but we'll just work with these examples. And end behavior is very, very specific language, and it'll be along these lines. As x approaches -infinity, whatever the name of the function is, we'll call it m of x this time. We say, what does m of x approachate? In other words, approach. What does the y coordinate move to? When x approaches infinity, what happens to the y coordinate on the graph? We'll say m of x approaches, because that's the name of the function. So let's look this through. As x approaches -infinity, we are riding this leftward arrow. And what does it look like the y coordinate? What's it look like the function value is doing? It is getting closer and closer to 0. So for our first piece, for function m of x that's graphed here, as x approaches -infinity, m of x approaches 0. And look at this. Same concept is happening here. We're approaching from, quote, above as opposed to approaching from below over here. But again, as x approaches positive infinity, m of x, our function, approaches 0. And so this is specific language. What you see there, as x approaches -infinity, m of x approaches. As x approaches infinity, m of x approaches. In this case, for these two things, which looks like, by the way, what type of function? Looks like it's a variation of the 1 over x function, the reciprocal function. That's one of those 6 functions that you were asked to memorize as we worked into this unit. In our second function, we have something, by the way, we'll call it n of x, and it sure looks like a x cubed type of function. What's our n behavior look like? Well, as x approaches negative infinity, this thing is doing what? Still going down. The y-coordinate is approaching negative infinity. N of x, when you evaluate the function, that's the same as the y-coordinate. N of x approaches negative infinity. And on the other side, what are we noticing? As x approaches infinity, as we keep going further to the right, we do what? We also keep getting bigger and bigger. Our function approaches infinity. One more to work with. And our last part is, notice that we have a terminating dot here. So our n behavior is limited to what? Just moving in the positive infinity direction. We'll call this function p of x. And what can we do? Well, as x approaches negative infinity, it doesn't approach negative infinity. This thing has a termination at what? X equals -3. By the way, this little fishhook thing looks just like a square root function that's been shifted a little bit. Back to our n behavior, as x approaches negative infinity, there's no approaching negative infinity in the first place. This is not applicable. There is no end behavior because I never approach. My x-coordinate's never going to approach negative infinity. There is rightward end behavior, however, because of the arrow that you see here. And as x approaches infinity, p of x, this function, it's getting bigger and bigger. What's that tell us? P of x approaches infinity. So there's everything. Increasing, decreasing, answers in terms of the x-coordinate. Local max, local min, provide your answer given me point location, xy coordinates. Absolute max, look at all your local maxes, local mins. Try to figure out, do you have a biggest of the big, a smallest of the small? Maybe you will, maybe you won't. It all depends. Zeros. Zeros are given as x coordinates. Comparison to 0 are given as intervals. Give your answer in terms of the x coordinates for both of those. And end behavior, which we just did last. Remember the specific language we're looking. What happens to the function? As x approaches negative infinity, the function approaches what? As x approaches positive infinity, the function approaches. Remember to give the name of the function as you work through this point. Your first language is always as x approaches negative infinity, as x approaches positive infinity. After your comma, just put your function name, approaches whatever value you see, and you're good to go. So there we are, the first part of section 2.3.